Okay, guys, 8.3, the age of the solar system. So this section is about, it's the last section, and it is about how old our solar system is and the things inside and how we know this. Okay, so first thing, how in the world can you tell me how old the world is? Like, how do you figure this out? Okay, so first off, let's start off with how old the solar system is. It's about 4.5 billion years old. 4.5 billion. Okay, so first, let's talk about, well, how do we figure out how old, like, fossils or bones that they find? How do we figure out how old these things are? We do something called radiometric dating. And what that means is, okay, you have in our bones right now, we have something called carbon-14, okay? And we create this carbon-14 by eating different things, and then it replenishes our bones and makes sure that we have a lot of carbon-14. When something dies, it no longer can replenish itself, and that carbon-14 switches to carbon-12. Which means it's the number of electrons are changing. Yeah, we have things that are isotopes switching into more stable atoms. Well, what we can do with a bone is if you find a bone of a dead animal, you can somehow, okay, you use a machine, you take a portion of it, a sample, and you see how many carbon-14 atoms it has and how many carbon-12 atoms it has. Okay, and then we look at current animals and we say, okay, well, this type of animal should have this many carbon-14 atoms, but it only has, this bone we dug up only has this much. So that means it's lost this many carbon-14 atoms, and based off of that, we can determine how old an object is. Okay, and that's radiometric dating. So, just a more scientific way of saying it is some isotopes decay into other nuclei or atoms, okay? And this half-life is the time for the half-life of nuclei and the substance to decay, for the amount of time it takes for it to decay is the amount of time that we can determine how old it is. Okay, so let me draw something out, okay? And let me get my pen. Okay. So, let's say I got a bone. Okay, I'm going to stick with my bone idea. Okay, so I got a bone. It's like a dog bone over here. Okay. And let's say normally it should have 20 carbon-14 atoms. Okay, let's say normally it should have 20 of them in this sample that we've collected. But we went and found this other bone, okay, and we realized that it should have the same 20 of them, okay? But we started looking at it and we realized it doesn't have 20, it only has 5 carbon-14 atoms. Okay, so it only has 5 of them. That means 15 of them have disappeared. Okay, so, well, not disappeared, but decayed into carbon-12 atoms. Okay, so let's look at half-lives. Okay, so now why these atoms deteriorate in half-lives, I'm not too sure. I'm not even sure if we know the answer to that, but let's say we got 20 of them. Okay, a half-life means half of them survive over some amount of time. So the first one, if half of them are going to survive, then that means 10 of them would survive, right? 10 carbon-14 atoms survive. Okay, now let's say it has a half-life of carbon-14. I don't know it off the top of my head, but let's say it has a half-life of... And these half-lives will be given to you, okay? All the different isotopes have different half-lives, and they take, some could take milliseconds, some could take several billion years, okay? So let's say this one has a half-life of 2 million years. Okay, so that means that I'm sorry, I messed that up. It's my pen's writing so slow. So that means for it to switch from 20 carbon-14s to 10 carbon-14s would take 2 million years, okay? So if there was 10 in here, we would say, oh, well, it's 2 million years old. Okay, but we have 5, so let's do another half-life. If 10 was cut in half, we would have 5 carbon-14s, okay? Carbon-14. And that would take 2 million years, right? Okay, so we could say this bone is 4 million years old because it's gone through the half-life twice. Let's go a little further. Let's say instead of seeing 5, or let's say we dug up another bone. And they counted how many there were, and there was 1.25 carbon-14s. Okay, I know that sounds weird, but remember there's a lot of these. Like we're talking thousands and thousands and thousands of these carbon-14s. I'm not saying that there would be 1.25 of them. Okay, so let's say we have 1.25 carbon-14s, and we see how old this bone is. Okay, well, let's cut 5 in half again. So its half-life would be 2.5 carbon-14s, right? And that would have taken 2 more million years. Okay, and then so we're still not at 1.25, so we would cut it in half again. Okay, so it would be 1.25 carbon-14s. Okay, and then that took 2 million years as well. So that means that this took to go from 20 carbon-14s to 1.25 carbon-14s. It would take 2, 4, 6, 8. So this bone is 8 million years old. Okay? So that's how we do radiometric dating. Now, depending on what it is we're radiometric dating, we're using different types of isotopes. Like on bones, we use carbon-14. Well, so what you need to do, if you want to figure out how old the Earth is you want to grab a bone or something that was formed at the beginning of the solar system and hasn't been messed with. Okay? The reason why you have to grab something that hasn't been messed with is it's kind of like with these bones. If it's been messed with, it's like the animal was alive. They were eating something. They were adding carbon-14 to their bones. So you need to find a rock that hasn't been messed with since the beginning of the solar system. Okay, where could we find a rock that hasn't been messed with since the beginning? Well, there's a lot of them. They're just not on Earth. They're in space, asteroids, right? Planetesimals from the beginning of the solar system, right? So if we can get our hands on those asteroids, we have a rock that hasn't been touched. And we can do this radiometric dating. Not with carbon-14 atoms, but with some other isotope that would take much longer to decay. Like we use carbon-14 in bones because it takes some small portion of time to figure it out. So we can figure out like if an animal's been dead for so many thousands of years. Okay, if you want like a rock. Let's say you try to use carbon-14 for a rock. I don't think it's going to have carbon-14, but let's say you do that. If you get a rock from the beginning of our solar system, well, it would have gone through so many half-lives, there wouldn't be anything left. So you wouldn't be able to use it to radiometric date. So you need to find an isotope that takes longer for a half-life, so it'll have more stuff inside of it, and we can count it, okay? So we did this with and I will go back to that question right now. We did this with old meteorites, and we used uranium dating, which means uranium takes a half-life of it's billions of years, okay? So that means it's easier for us to count how many are left. And from doing this with these old rocks and things, and look, they did this with the moon as well. They figured out the moon was about 4.4 billion years old. And then we did this with meteorites, and it came out to 4.55 billion years old. And we've done it with, so that means that the planets were formed somewhere around that same time of 4.5 billion years old. So that's how old our solar system is. Now, we assume the sun is about 5 billion years old because it formed a little before. The planets accreted together. But that's how we come up with this. So our solar system is about 4.5 billion years old. We have proven this over several times with different meteorites and different rocks that we find. So we know this is an accurate number. Okay? So let's talk about, let's do this with a problem here like I would ask on the homework, okay? Because I want you to be able to get these right. Okay, suppose you find a rock that contains some potassium-40. Okay, so that means that is the isotope they're looking at. Kind of like how with bones we look at carbon-14. Okay, well, they're looking at potassium-40. It has a half-life of 1.3 billion years. Okay, so that means that if you had like 10 of them, if you now count 5, then it went through one half-life, and that took 1.3 billion years, okay? Okay, so you measure the amount, so here, an important thing to know here is the half-life, so let's underline it real quick. I don't really care about what type of isotope it is, okay? Because they're telling me the half-life of that isotope. Okay, you measure the amount and determine that there's 5 grams of potassium-40, okay? So that's how much we have now. By measuring the amount of its decay product, argon-40, so that's what it decayed from, the present in the rock, you realize that there must have been 40 grams of potassium-40 when the rock solidified. How old is it? Okay, so we went from having 40, okay, so we started with 40, like that's what it should have had at the beginning, and we worked our way down to 5 over time. So what you would do is do half-lives until you get to 5. So let's do half of 40. That would be 20. Let's do half of 20. That would be 10. Half of 10. That brings me to the number that we need, which is 5. So it looks like we went through a half-life 3 times. Each one of those half-lives took 1.3 billion years. 1.3 billion, 1.3 billion, 1.3 billion. Okay, so in order for, we can determine that this rock that we found is 1.3 plus 1.3 would be 2.6, plus 1.3 would be 3.9 billion years old. Okay, we can determine that's how old that rock is. Okay, so that's how you use half-lives. And that's how we determine how old different things are. By looking at isotopes, looking at how long it takes for half of them to decay into other particles, and we use that in science. I hope you enjoy learning about half-lives. That's all of Chapter 8.